Hello, today we will discuss one of the important problem in quantum mechanics called particle in an infinite potential well. This is a foundational problem to understand quantum mechanics better, and this is a starting point for solving more complex problem in quantum mechanics. And using this one can understand easily the wave particle duality, quantization and the boundary conditions, many things in quantum mechanics very easily, and most of the results of this topic can be directly applied to a material called quantum dots. It's a quantum dots is a semiconductor particles in which electron to move in a narrow region of space. This is exactly like a 3D particle in an infinite potential well. So let's discuss this topic in detail. This is the pictorial depiction of the problem. Here the particle is allowed to move in a region between 0 to A, and within this region my potential is 0, and at x is equal to A, x is equal to 0, my potential is infinity. And this is how we represent this potential structure using equation. As you can see from here, between 0 to A my potential is 0, and when x is less than or equal to 0 and x is greater than or equal to 0, my potential is infinity. So applying the Schrodinger equation, this is time independent Schrodinger equation. Applying this equation to this region, we get this equation. Here v is equal to 0 within this region. So altering this equation gives this, and substituting for 2me by h cut squared as k squared, we get the fourth equation is this way, and solving this equation we get two solution of this kind. And again this solution can be simplified using de Moivre theorem, and this is the solution of the equation 7. And there are two independent solutions as you can see here. This is a second order differential ordinary linear differential equation with a constant coefficient, so there has to be two different independent solution. Those are all this. And what is specific to our problem, that we have to choose it from the boundary condition. We know the wave function at the boundary at x is equal to A and x is equal to 0 is 0, since potential at these places is infinity, so particle can't be there. So applying this boundary condition means applying the boundary condition at x is equal to 0 as 0, we get this equation. We know sine 0 is 0, so we have b only, and that is equal to 0. So b in this equation is 0, so we have only this term, one solution. And applying the second boundary condition gives a sin ka is equal to 0. So when this is true, whenever ka is equal to n pi, so k is equal to n pi by a. Substituting the value of k into the solution of Schrodinger equation gives me the unnormalized wave function of particle in an infinite potential well, which can be normalized with the notion that mod psi squared represents the probability density of particle, and mod psi square in 3D represents the probability of finding the particle within a unit volume, and in 1D case it represents the probability of finding within unit interval of space, in unit interval of length. So integrating over 0 to A, and this probability density should give 1. This represents within the box somewhere particle exists. Okay, next, so doing the integration, since a squared is constant, it will come out from the integration, and integrating this factor, we know sine squared x is equal to 1 minus cos 2x by 2, and putting that and doing the integration and breaking the interval means bracket gives me this equation, and doing the carrying out the integration gives this. And here you can see the second term, in place of x if we put a, we will get sine of 2n pi, which is 0. Again in place of x if we put 0, sine 0 is 0, so this term will be completely 0, and this gives me a squared by 2 into a is equal to 1. So solving this we get a is equal to square root of 2 by a. Putting this into equation, solution of Schrodinger equation gives the normalized wave function of this. This is the normalized wave function of particle in an infinite potential well. This is also called the eigenfunction of the system. Okay, now solving for so we know k is related with energy, and squaring this we get this equation, and we know k in terms of energy can be represented as 2me by h cut squared, and putting this and rearranging this we get the energy eigenvalues of the particle in an infinite potential well. So here n squared is the energy quantum number. N is equal to 1 represents the ground state energy of the particle, and n is equal to 2 is the first excited state, and n is equal to 3 represents the second excited state of the system. Now here you can see a squared is appearing in the denominator of the energy expression. That means if you widen up the box, the energy quantization means the quantized energy is going to decrease. So when you widen up the box more and more, the energy quantization, the spacing between the energy will get reduced, and finally it will go to the continuum limit. So to understand the energy quantization bit more, let's consider this equation and find the substitute for n is equal to 1 gives the ground state energy as this, and substituting n is equal to 2 gives the second excited state in terms of the ground state energy, and that is 4 times the ground state energy. And third excited state, no, third state is equal to 9 times the ground state energy. So nth level energy is equal to n squared times the ground state energy. So plotting this energy gives a clear picture about the energy quantization. Here if this is E1, so second excited state energy will be 4 times the ground state energy, and the third energy level will be 9 times that of the energy of ground state, and for fourth energy level will be 16 times the ground state energy. So let's further understand the nature of the wave function. So this is the ground state wave function. This we obtain by putting n is equal to 1 in the generalized energy eigenfunction of the system. And here is a plot of the psi 1 as a function of x. As you can see here, the psi 1 takes the maximum value at the center of the box, and the corresponding probability density plot shows this profile. Here you can see the mod psi squared, just a square of this function here is shown here. Here this represents the probability density, and probability density is maximum at the center of the box. Now consider the second level energy function. Here the first excited state wave function is given, and is the plot of the psi 2 as a function of x. Here you can see there is one node at the middle of the at the center of the box, and squaring this we get the probability density plot. You can see here the probability of finding the particle at the center of the box is now 0. It is complementary to the ground state probability density plot. Here you can see the center of the box has the maximum probability, but here at the center of the box the probability of finding the particle is almost 0, roughly 0 here. So you can see here in the wave function plot, when you plot the nth excited state energy, there will be n minus 1 nodes within the box. So here you can see the first excited state has one node at the middle, and third will have two nodes in between 0 and a. Likewise the nth excited in the nth level wave function will have n minus 1 nodes within the box. That's all. Thank you.